Inflation has been a hot topic recently. In today's talk, I'll talk about inflation in the cost of garbage collectors, how we got into this situation, and how we can fix it. So please feel free to interrupt if you have any questions. So what is garbage collection, or GC? GC provides automatic memory management by identifying reachable objects and reclaiming unreachable ones. It provides productivity and memory safety compared with manual and error-prone memory management such as malloc and free. You can find languages with GC from mobile devices to servers. Since the first few GC algorithms such as reference counting and mark sweep invented in 1960, we seem to have been making great strides and GC is becoming ever cheaper. Now we got sub-millisecond pauses, great improvement in heuristics, and many different algorithms to choose from for your need. Now, can anyone guess how much does GC cost in terms of percentage? Anyone? 127. So, despite the popularity of GC, its cost has been a pretty unclear and sometimes contentious topic. So in this graph, we measure the total computation overheads of 5 production GCs in OpenJDK 17 running decoupled benchmarks. Because fundamentally, GC is a time-space trade-off, we show the overheads of GC in different heap sizes relative to the minimum heap size required to run a benchmark. So towards the left, you have a very tight heaps, only 1 or 2 times the minimum size required, and towards the right, you have very generous heaps, 6 times the size required to run a benchmark. You can see that different collectors demonstrate different trade-offs. Serial showing black, right at the bottom, despite being a very simple collector, performs the best. It does all GC work using a single thread, so it avoids the synchronization overheads that other collectors have to pay. Overall, you can see this clear distinction between 2 groups of collectors, the old ones, serial parallel and G1, and the new ones, Shenandoah and ZGC at the top. If we look at the year each of these collectors was introduced into OpenJDK, it is alarming. We are going backwards. The newer the collector, the higher the overhead. So at 2.5 times the minimum memory required, which is a modest provision of memory, depending which collector you use, you're paying 6% to 92% actual CPU cycles just to run GC. The newer collectors are more costly than the older ones. What's worse, the methodology used to measure the cost actually gives an underestimate, so the real cost can be even higher. I will come back later as to how this methodology works. Let's switch gear a little bit. Suppose you have a slow GC. How would you go about debugging it? One tool we have is sampling. For every X nanosecond, we can take a look at what's running. This gives us a statistical profile of the program execution and allows to relay slower execution to some code. But fundamentally, it will not allow us to establish causal links. One of the sampling tools you can use on Linux is perf. Let's look at what perf can help us out GC. The top 3 methods are scanning plain objects, scanning object arrays, and iterating over regions of the heap. Great, very insightful. Of course, I'm being sarcastic. There's nothing surprising about the transit closure of the heap accounting for most of the GC cost. What about we look at the GC logs for some insights? Well, first of all, you need to find the needle in the haystack. And before long, you'll find yourself needing a parser to make the job easier. Turns out parsing GC log is harder than what you might expect, and the parser that can parse 50 uploads a month costs $50. What's worse, every time when you want to log something different, you need to change the code and recompile the VM. And what's next? Well, of course, you need to change the parser as well. At this point, you might feel very disheartened. If this happens on the state-of-the-art production GCs, what we just saw should give GC researchers and the broader PO communities a pause. At this point, I want to emphasize that this is not a critique of the developers of these systems, but a critique of the broader PO community from which this emerged, which includes myself. In this talk, the main takeaway I want you to remember is that GC innovation is impeded by lagging methodology and tooling, which are no longer fit for purpose. And I will talk about how we might address these gaps. First, let's look at the methodology. For too long, a very simple metric, very simplistic metric that used to measure the cost of GC, which is looking at how many seconds the GC is running. This prevents us from recognizing the significant regression in GC costs, as we have seen earlier. First, a collector that uses a lot of threads might collecting faster in time, but burns many CPU cycles. This not only increases energy consumption, but also leads to opportunity cost, because you could have saved some cycles and run other applications on the same machine. Second, with the increase in concurrency with respect to application or mutators in modern GC, GC can also compete for cache capacity, memory bandwidth, and etc. This kind of cost is not covered by just measuring how long the GC has been running. The second problem I will talk about is tooling. As we have seen earlier, although sampling and logging are useful in certain scenarios, they are not adequate. A key problem in most GC is a lack of observability. You cannot ask arbitrary questions without having to know ahead of time what to ask. And I will give more examples about this later. All hope is not lost. In this talk, I will talk about how to improve the methodology and tooling. We proposed a new methodology called distillation and allows us to measure the real cost of GC. This was joint work with my PhD advisors, Steve Blackburn, Mike Bond, and Martin Mas, and was published in ESPAS 2022. We also proposed that we integrate tracing to improve the observability of GC. This was joint work with Claire Huang, who is an amazing undergrad student from the ANU that I have a privilege working with, and Steve. It was published in MPLR this year. So first, let's look at what not to do when measuring the cost of GC. A straightforward approach is to figure out when the GC starts and ends. And we mark all the costs during GC time in yellow, and the rest is just application. Simple, right? So at the top, we have a very simple GC. Every time when the heap is full, the GC has to traverse the entire heap. So you see these two long yellow blocks. In the middle, we have an improvement, a generational GC. You can collect a subset of the heap at a time. So each GC is much quicker, but you don't clean up as much memory, so you have to do a lot more GCs. Finally, you have no GC. It is not very practical. It only allocates memory, but does not do any collection. So you see no yellow chunks as expected. Are we done? Are the yellow blocks the GC cost we want to know? Unfortunately, the reality is a lot more nuanced. Can you notice any difference on this slide from the previous slide? Well, they basically look the same. You're right. The only difference is that now each row is covered by a very subtle yellow overlay. They represent the GC costs that are very hard to separate from the application. Why is this so? For example, depending on the GC algorithm, different logic is required to figure out where the free memory is to allocate new objects. You might also have barriers, which are code snippets to mediate heap access to help the GC monitor changes to the heap. Allocation sequences and barriers are often aggressively inline into the application code by optimizing compilers, and it's incredibly hard to separate the cost from the application. Apart from this direct cost, GC can also have indirect cost. For example, after GC finishes, application will resume as a code cache, and that slows things down. GC can also bring indirect benefits. For example, GC can move objects to reduce heap fragmentation and improve spatial locality of the program. Things get even trickier when GC runs concurrently with the application because of contention of hardware resources and so on. But what if we know the ideal cost to run the application that includes the potential benefit that the batch GC can bring, but exclude all the GC costs, include the implicit and explicit ones? Then we can simply subtract this ideal cost from the total cost, and the difference will be the real GC cost. Of course, we don't know this ideal cost, otherwise I don't need to give this talk. Fortunately, we can approximate this ideal application cost. We call this method distillation. Just like when you have a mixture of different liquids and you want to remove one, you distill the mixture. The total execution cost is a mixture of GC and application cost. We are trying to remove as much GC cost as possible. So how do we do that? So first, we measure the performance just like before, and identify and subtract all the explicit GC costs, the yellow blocks we saw before. We remove this explicit GC cost from the total cost, and what remains is not spirits, but we call distilled application cost. This distillation is not perfect. As you can see, that we still have this yellow overlay on top of the blues. They're only approximations of the ideal cost and are always larger. We choose the best of this as our baseline because it best approximates the ideal cost, and we call this the minimum distilled application cost. Note that the GC that achieves the minimum can vary depending on the benchmark. We then compare the total cost of each GC with its baseline, and we subtract the baseline from the total cost. And boom, the difference, the red blocks here, is what we call lower bound overhead, LBO, or we pronounce it elbow. It's an empirical lower bound on the cost of each collector because the costs measured this way are always smaller than the real GC cost. A nice thing about this methodology is that it's very simple and can be applied to different programming languages, and the distillation process is orthogonal to the cost metrics we care about. You can measure work clock time, CPU cycles, energy consumptions, and so on. It is important to note that elbow is not the same as normalizing to the best GC or to no GC. A simple normalization is shown in the right only tells you how different GCs compare. However, on the left, elbow reviews the GC cost, including the cost of no GC due to its bad locality and frequent physical memory allocation. Now we look at tracing and how it can help us debug GC performance and improve observability. Let's look at a simple example of a GC worker loop. At the start of the loop, a GC worker gets new work, possibly by work stealing from other worker threads for better load balancing, and then execute the work, rinse and repeat. Now suppose the GC is slow, what can we do? Well, maybe individual work takes too long to execute. How do we verify this hypothesis? Easy. We start the timer before we do the work and measure how long the work takes and output the difference in the log statement. Of course, you now need to recompile the whole system. And if you have worked on any large-scale production system, the compilation isn't exactly fast, which gives the perfect excuse to slack off. And 1 hour later, your code finally finishes recompiling. You run the program again. Oh no, the numbers tells you that individual work is actually fairly fast. So go back to the drawing board, ask yourself another question. What if the work stealing is slow? Well, great question. Let's find out. What do? Well, we move the log statements around and measure again, and compile again. This kind of workflow not only wastes developers' time, but also leads to significant cognitive friction due to time between you coming up with a hypothesis and when you actually get to test it. So how can tracing help us? Well, instead of baking the decision of what to measure into the code base, you instead declare events with parameters indicating the context. And you can write different tracing logic against the same binary. No recompilation is required. You can even trace the existing running program, which is great for troubleshooting production servers. And I can talk more about the technical details underlying it during the break. So what can you do with tracing? For example, you can count every event. Every time when do work happens, you increment the counter. And at the end of the program, you can print the counters out. You can know how many times the worker loop has been executed. Suppose you now want to ask a different questions, such as how long it takes to get new work by calling pull, and what the distribution looked like. Well, it's simple. Every time before a pull is called, you record the timestamp, and then before you actually start doing the work, you look at timestamp again, calculate the difference, and add it to a histogram for a particular type of work. And then you can associate that distribution for different types of work by accessing the argument. And at the end of the program, you can now see the distribution of time needed to get new work for each type of work. With the same set of events, you can just store the timestamp of each event and visualize them in a timeline, which can give you a lot of insight into the execution of the program. My apologies for the color scheme, which is not exactly very inclusive, because but this is the default color scheme used by Perfecto, so my apologies for that. For example, this is a visualization of one GC during the execution of the research benchmark. Different types of work are assigned different colors, and one row is one GC worker thread. You can see that the load balancing of GC worker is only good in the beginning and becomes very poor towards the end and becomes basically serial execution. And when you zoom in, you can see that in the later part of the GC, there is only one thread executing a series work of identical sizes. Further debugging reveals that this is caused by the research benchmark not closing files, and each open file is recorded internally by OpenJDK in the linked list, limiting the GC tracing parallelism. This was only possible because tracing allows to exhaustively process every single event, establishing causality, not just correlation. So what's the takeaway? GC innovation is curtailed by lagging methodology and tooling. A significant regression in GC overheads has gone unnoticed, and GC performance is very hard to debug. In response, we first proposed the distillation methodology. It exposes the opportunity cost and concurrency overheads incurred by parallel and concurrent GCs. That is not easily seen if we only measure the work clock time of GCs. Second, we encourage developers to integrate tracing, a very powerful debugging tool, into GCs. It can give us structured, high-fidelity measurement that retains the execution context. It also gives us the flexibility of changing tracing logic without lengthy recompilation. That's all. Thank you.